Engstrom critiques laws of form, Appendix 2, about about the statement all A or B. And I just want to point out that if you, in the kind of hard to see gray, it says supplementary PDF, which is a link. And if you click that link, you will get, Florian was kind enough to post it, and it looks like this. And so here the title, Engstrom on all A or B, and so on. Now, and so the theme of what I'm going to say is that regarding the truth of all A or B, we should separate possible versus necessary conditions. And then I have come up with laws of form notations for what I call the logical matter. So let me, as it turns out, I'm going to actually use the three diagrams that are in this 6-page link, and let me go to those right now. So I want to make this bigger, and this is one of 3 hand-drawn diagrams. So sheet number 1, and my goal was to discover what I call the logical matter of the universal statement all A or B as premise from which valid deductions may be drawn. So the logical matter underlying valid deduction. And I decided that this logical matter is most clearly shown and known in what I label an Euler diagram, which shows all 2 to the n logically possible subsets and selects some subset and states that this particular subset is either empty, no member, or exclusive or may contain some existence as a member. And I say that this is the bedrock logical matter of the statements used in syllogisms. Now, and thus I do not agree with Spencer Brown that, quote, it's no use appealing to graphical forms such as Venn diagrams. So I don't agree with that. And I thank you very much, Lou Kaufman, for your Wheel of Syllogisms, which has been very important to me. Now let me read from the conclusion of my 6-page link. I claim that all A or B is true exactly when A is a subset of B is true, the subset relation, which is when A minus B, or A intersection not B, is necessarily empty, and when existences are allowed, that is possible, in a subset, whenever the subset is not necessarily empty. So we have this hierarchical coupling of a modally necessary and modally possible conditions. And I take that to be the logical matter of the situation. Now, if we look at this diagram, if we start off with the statement all A or B, which actually more rigorously is all A, if any exist, are B. And Spencer Brown represented that as in Barbara syllogism, as what I'll describe as A cross B, which is shown as number 2 there. Now, Engstrom interprets that right angle as the subset relation. And then I convert, and so therefore I write that subset relation using capital letters for sets as opposed to lowercase letters for members. So we have A as a subset of B, and we want to know the conditions for the truth of that. I put the T for truth. Now then, I take consequence, I think it's 6, extension, and I use capital letters for sets, and I interpret it as a set statement. And you can see the, A equals A cross B cross 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 all, and then A cross B cross cross all. And then I diagram those in this Euler in a part of an Euler diagram that only shows set A, but it shows set A bifurcated by set B. And so, the one term, on the left is the crescent on the left, and the A cross B cross all corresponds to this vesica, which is interpreted as A.intersection.B. So we have this disjoint union of A minus B with A.intersection.B. And then I use this notation having N for necessarily the case and T for true. And the necessary condition for the truth of A as a subset of B is capital N. It's necessary that the set A minus B or A minus A intersection B cross, B complement, is empty. And the modal truth of that describes the necessary condition for A as a subset of B. And then for the vesica on the right, I have T for true. It's true that it's possible that there exists an X, a member, that's an element of A intersection B. And so I claim that these two logical matters, modally different but separate, constitutes the logical matter for the truth of A is a subset of B, and that is exactly the logical matter of the universal affirmative statement, all A or B, all A, if any, are B. And so that's basically what I've come up with. And then I go to the next, let me scroll down. Oh, I have to, let's see now. Yeah, now I scroll down. Oh, I want to go to the one on the right, which you can't see in my thing because of it's overlaid by the people. So anyway, the sheet that can people see the right hand one of those? That's a question.
Yes. Yeah. Yes. Yes.
Okay. Yeah. So you can see it's not covered over by the
No, that's only how it's represented on your screen. We see the full screen.
So basically, there's the left hand. Oh yeah. So here I show the laws of forms that I use to represent empty and non-empty logical matter in syllogisms, in particular with all A or B. And so I start with, let's see here. Yeah. Okay. Well. Okay. So okay. So yeah. So let's look at the word on the right, and I start with this A intersection B, and Spencer Brown represents that by A cross B cross all. And that's normally conjunction, but here it's the set intersection. And I append Spencer Brown's thing by saying possibly there exists a member in A intersection B. And that corresponds to possibly some A as B. And then that's the laws of form notation for it. But I'm basically implicit in the A cross B cross all. I actually write P for possible that there exists an X, it's an element. And so we have a three depth 0, 1, and 2, and the A and B are in depth 2, but the expression A cross B cross all is in depth 0, and in depth 0 I implicitly write it P exists X in that. So this is the default situation that you can, whenever it's not disallowed, it's possible to have an element in that subset. So, but now I want to get to the how to represent empty subsets. So if we go to the left-hand side, left-hand column, we start off with the universal affirmative, all A or B, and let me call A the subject and B the predicate. And Spencer Brown represents that by A cross B. But all A or B can also be restated as a universal negative. No A is not B. The negative is no, but then you also have to say double no. So no A is not B is another way of saying all A or B. But how to represent that in laws of form notation? We simply do reflection on the predicate, and so the B becomes B cross all, and therefore you end up with the universal negative as A cross B cross cross. Now, one can actually parse this by the A cross stating there does not exist an A such that, and by taking a membership symbol and invert it, and so then you're saying with this laws of form expression, there does not exist an A that's an element of not B. And so this stating it that way explicitly states the non-existence of a member, small a, that's an element of the complement of B, of not B. So this is the simple way of expressing the left hand, that the left hand in the Euler diagram, A minus B, A intersection B complement, is empty. But there's another way of having a laws of form expression to indicate that that set is empty. And this one will align with Spencer Brown's notation for some A is B. And that is by using reflection again. And this is the middle column. The middle column, you cross all and cross all again, and that's the reflection. Well, the first cross all gives you back the intersection set of A intersection B complement, which is the left-hand part of the form of extension. But to show that it's empty, we cross all again, and that cross all is simply a negation. But it's a double negation, because we started off with the default of capital P with the existence sign, which P is the modal possibly exists, the P existence sign. It possibly exists a member in A intersection B complement. But this final negation negates both the mode and the statement of existence, and converts this default possible membership into necessarily no existence. Necessarily, there doesn't exist, it's not possible to have a member in A minus B. And so this is my laws of form notation for this empty necessary condition for both A as a subset of B and for all A or B. And when one goes to the extension, which shows the disjoint union of the two subsets of set A, one necessary and one possible existence and one necessary no existence. The fact that the A minus B is empty means that set A equals set A intersection B. Now, this becomes important when you're actually trying to find out one of the meanings of Barber. Anyway, so the left-hand column basically does the same thing. It shows the disjoint union of sets as a bifurcation of set A. It shows this default possible existence for a subset, and then the negation of the left-hand side, which is A minus B. And so that gives you that necessarily the A minus B is empty, and therefore set A in practice equals set intersection B. And so Barbara is the negative half of Barbara. It has to do with the empty sets, and that's a necessary part. But then the set membership of Barbara is A equals A intersection B. That's premise one, I guess, and then B equals B intersection C. That's premise two, the positive half. And then you substitute B equals B intersection C into A equals A intersection B, and you get A equals A intersection B intersection C. Well, now Barbara is very obvious. If there's an element in A, then that element happens to be in this 1/8 of the whole space, which is A intersection B intersection C. But therefore, A is in C. So we go from all A is B, conjunct all B is C, to the conclusion, which is obvious from the Euler notation, that all A is C. And that's the what I call the membership half of that, assuming that there is a member of a subset. And so these two logical matters, necessary and possible, illuminate the two aspects of this syllogism Barbara, and they also apply to when you have particular affirmative and particular negative. And Liu shows this in his Wheel of Syllogism, which is a wonderful contribution. And I have come to articulate the logical matter of all A or B in three different languages, three different notations. This written, symbolic, modal, scripted language with the P's, the N's, and the T for true, and the sets, and the Euler diagram, which visually shows the sets, the subsets.
Just 5 more minutes, Jack. Okay.
Well, I'm done. And these specially interpreted laws of forms, in which each aspect of the logical matter is parsed. You can see where the existence lies, where the non-existence lies, where the set membership is in the depth 1 or 2 or 3, and the intersection symbol, an upside down U, is you can draw it in Spencer Brown's laws of form for some A or B. You use this thing here to connect this, and this, and there's the intersection. And so for me, this was a way of finding a bedrock. And I do want to be able to see more clearly how Appendix, the interpretive theorems 1 and 2 can be mapped onto similar logical matter. That's for the future. But here I've simply done it for all A or B. And so for me, I'm very content to have found this bedrock logical matter from which you can use these three languages, including a laws of form notation, to see what's going on in the syllogisms. And thank you, Lou, for your wheel of syllogisms. And that's it. I open to questions.
All right, let's thank Jack. Yeah, Lou.
I just wanted to mention that one part of the way you're thinking here should be emphasized for all of us, that it's kind of been in the background, and that is that the Venn diagram, which is never mentioned in laws of form and so tends to be outside the discussion, is absolutely fundamental to thinking about the algebraic identities in laws of form, which is one of the things you were doing at the beginning. If you take a two-circle Venn diagram and you have A intersect B, and then A gets bisected by B, and then though you write down what that bisection is, you find that you're looking at the form of extension, precisely. And many other identities in laws of form are precisely interpretable in terms of the Venn diagram, so that the Venn diagram should be understood as a realm of imaginary values in which all of the identities in laws of form are instantiated. And they also stand for all of the different possible states of affairs involved in doing syllogisms or any other form of reasoning. So they're really the basis for thinking about reasoning altogether. And it's kind of a shame that we have never talked in most of our discussions about Venn diagrams, perhaps just because they were in the history and Spencer Brown was assuming that everyone who read him knew about them, I think. That's a long comment. It's not exactly.
Yes, this is and Lou's work has been crucial for me in sorting out, but at some point I have to say, well, what do I believe in laws of form? And I don't believe that it's no use appealing to graphical forms. So for me, part of the sanity was to be able to sift the wheat from the chaff in laws of form, to negate something he says that in some sense clarifies the wholeness of it.
Very good. We can open up to more questions in the room or on Zoom.
I've got one thing
Go
about
ahead, Lyle.
Barbara. You say all A are B. Now, all A seems to indicate a set, but B seems to indicate an element. And so if you're saying that all of the elements in the set of A are B, then you've got that everything in A is the same because it's the same as B, which means that you just have one element in A, which is equal to B. So the problem is the contraction of reference beyond, to the point where you can actually follow it. So,
right.
Yeah.
Lou?
I'd like to comment on what Lyle was saying. This is an example of how we speak. We indicate a context A, and then we indicate all of the members of the context of A, and we go back and forth without any indicator of the end of that switch when we speak. And I don't think we can avoid it, but sometimes we want the indicator there.
Well, but the point is that what we're really saying is that all A have a characteristic B.
Yeah.
And
So B, when we say B, sometimes we mean the context, the characteristic B, and sometimes we mean the element. And it's all over our language, and it's all over our mathematics. We refer to as the set of all prime numbers. Which one did you mean?
exactly. And also, this is better done in color. If you use the green the green cross, then this thing, you don't need to have little squiggly lines joining crosses. It works out pretty well, and it's in the slides of my presentation.
Yeah, and then you interpret it properly as you do in that context.
Yes, exactly.
Yeah.
And,
All right.
and you can have you can do the sets either as unique items, or you use the von Neumann notation. You can make sure that every element in your set is unique.
All right. That is all the time that we have right now, but let us thank Jack.
Thank you.